Hello and welcome to Chapter 4 on Atomic Physics and Spectra. To begin with, we're going to talk about black bodies radiation, which is radiation when what is essentially a black body, such as a piece of iron, is heated, and when the object is heated, the object's peak color shifts to shorter wavelengths as it gains a higher temperature. An ideal black body absorbs all of the electromagnetic radiation that strikes it. This incoming radiation heats up the black body, which then re-emits the energy it has absorbed, but with different intensities at each wavelength than it received. Furthermore, the pattern of radiation emitted by black bodies is independent of their chemical compositions. By measuring this intensity of radiation emitted by a black body at several wavelengths, it is possible to plot a curve of its emissions over all wavelengths. Ideal black bodies have smooth black body curves, whereas objects that approximate black bodies, such as the sun, have more jagged curves whose variations from the ideal black body are caused by other physics. On the left, you see an ideal black body curve where the higher temperature causes there to be a shorter wavelength, which corresponds to a higher frequency of its peak light, while there is also more overall emitted light. Whereas if you look at the sun, which is a 5800 Kelvin black body, or close to a black body, it has some gaps in this black body that keep it from being an ideal black body as we see on the left-hand side. In 1893, the German physicist and 1911 Nobel laureate William Wien showed that the peak wavelength of radiation emitted by a black body is inversely proportional to its temperature. In 1879, the Austrian physicist Joseph Stefan observed that an object emits energy per unit area at a rate proportional to the fourth power of its temperature in Kelvin. Lambda max is equal to 2.9 times 10 to the negative 3 over the temperature. So for the sun's maximum intensity is at a wavelength of 500 nanometers. Therefore, temperature is equal to 2.9 times 10 to the negative 3 over 5 times 10 to the negative 7th Kelvin, which is equal to 500 or 5,800 Kelvin. The Stefan-Boltzmann law states that the total radiant energy emitted by a black body is proportional to T to the fourth, or temperature to the fourth, where temperature is again measured in Kelvin. F equals sigma T to the fourth, where sigma is equal to 5.67 times 10 to the negative 8 joules per meter squared Kelvin to the fourth times seconds. The luminosity, which is measured in joules per second, is equal to F times 4 pi r squared, or sigma T4 times 4 pi I squared. So F of a hotter temperature of a hotter black body over F of a colder black body is equal to sigma times 10 to the times the temperature of the hotter black body, in this case 10,000 Kelvin, to the fourth, over sigma times 5,800 to the fourth Kelvin, which is about 8.8 for these two temperatures. Because these relate lambda and frequency to temperature, we can tell a lot about the object that we're looking at by the temperature, or we can tell the temperature of an object that we were looking at by looking at these peak frequencies, as is given by these different types of photons, or these different types of photon energies that you see here. In 1814, the German optician Joseph von Fraunhofer repeated Newton's classic experiment of shining a beam of sunlight through a prism. However, Fraunhofer magnified the resulting rainbow-colored spectrum. He discovered that the solar spectrum contains hundreds of fine dark lines, which became known as absorption lines because the light of these colors has been absorbed by the gases between the sun-emitted surface and the viewer on Earth. Fraunhofer counted more than 600 such lines, and today physicists have detected more than 30,000 of them. By the mid-1800s, chemists discovered that they could produce spectral lines in the laboratory. Around 1857, the German chemist Robert Bunsen invented a special gas burner that produces a clean, constant flame. Certain chemicals are easy to identify by the distinctive colors emitted when the bits of the chemical are sprinkled into the flame of a Bunsen burner. Bunsen's colleague Gustav Kirchhoff suggested that light from the color flames could best be studied by passing it through a prism. By separating the colors, scientists could see exactly which ones were present. The process of analyzing the spectrum of an object is called spectroscopy. Bunsen and Kirchhoff collaborated in designing and constructing the first spectroscope. This device consists of a narrow slit, a prism, and several lenses that strain the light rays and magnify the spectrum so that it can be closely examined. During some experiments, Bunsen and Kirchhoff examined the blackbody spectra of hot sources whose light they passed through a colored glass. Instead of seeing a continuum of wavelengths as they would have seen had the cold gas not been there, they saw dark absorption lines among the colors of the rainbow created by the hot source. The phenomenon is what Fraunhofer had earlier seen in the sun. The colored gases in his result were the atmospheres of Earth and the sun. In other experiments, when looking just at gases without hot sources behind them, they saw bright emission lines against otherwise dark backgrounds as noted above. Combining the results from both set of experiments, they discovered that the emission lines of a particular gas occur at exactly the same wavelength as the absorption lines of that gas. Today, instead of prisms, we tend to use diffraction gratings, which also cut light up into different colors depending on the frequency of the light going through, but are made up of a ton of tiny different slits which reflect back into a mirror and which are then measured by apparatus. And then the diffraction grating is a bunch of different slits which creates light in the same way that a CD scene creates light when light is shined on it, or peacock's feathers create light, not because of the pigments in their feathers, but because of the microscopic structure of the feathers. Again, looking at the absorption lines and the emission lines of a hydrogen sample, you see that the light that is absorbed by hydrogen is the same as the light that is emitted from hydrogen as it is burned. Kirchhoff came up with some laws to define this, which are going to be different from Kirchhoff's laws for circuits if you've taken an electronics or physics class, where Law 1 states that solid, liquid, or dense gas produces a continuous spectrum, also called a continuum, a complete rainbow of colors without any spectral lines. This is a blackbody spectrum. Law 2, a rarefied, opposite of dense gas, produces an emission line spectrum, series of bright spectral lines against a dark background. The light from an object with a continuous spectrum that passes through a cold gas produces an absorption line spectrum, a series of dark spectral lines among the colors of the rainbow. Answering the question of where these came from came as scientists began to understand the structure of the atom more. So in this experiment where alpha particles or radiative substance emits alpha particles which were shot at a gold foil, what was expected was that the alpha particles would go straight through unless there was a positive charge to deflect them. And then what ended up happening is that those particles mostly went through, but there were a few that didn't go through. And this came up with the ideal that there should be a small, dense nucleus which is surrounded by electrons rather than the plum pudding model which they had previously used, or which scientists had previously used, which stated that electrons and protons, or electrons and positive and negative charges, were going to be relatively uniformly distributed throughout the material. At this point, we're going to just go over quickly the four fundamental forces: the strong nuclear force, the weak nuclear force, which are two forces which keep the electron together, or the nucleus together, rather, which is why they are called nuclear forces, as well as the electromagnetic force, which keeps an electron orbiting around the nucleus, and the gravitational force, which is what keeps an planet orbiting around the sun. The number of protons in an atom's nucleus, called the atomic number, determines the element of that atom. Each different combination of protons and neutrons is called an isotope. Some isotopes are stable, meaning that the number of protons and neutrons in their nuclei do not change. However, many elements have isotopes that are unstable and become apart spontaneously. These isotopes are radioactive, as discussed earlier in the section, not really here. For examples, carbon with 6 neutrons, carbon-12, is stable, while carbon with 8 neutrons, carbon-14, is unstable, decays into nitrogen with 7 neutrons. To learn how radioactive decay is used to determine the ages of different objects, you can look in the book for Astronomer's Toolbox 4.2, Radioactivity and the ages of objects, but the ideal is that there is a constant which relates how long it takes for a nucleus to decay on average. So by looking at how many objects are still there, or how much of material is still one of these radioactive isotopes, rather than having decayed into a different material, you can tell the age of the object because you can know how much it has decayed in that time. Using radioactive age dating techniques on the oldest rocks brought back from the moon, astronomers are able to determine roughly when the moon was formed, 4.5 billion years ago. Applying the same technique to space debris on Earth meteorites, we can determine that the solar system, consisting of the sun and everything orbiting it, formed some 4.57 billion years ago. The number of electrons that orbit an atom is normally equal to the number of protons in its nucleus, thus making the atom electrically neutral. Astronomers denote neutral atoms by writing the atomic symbol followed by the Roman numeral 1. For example, metal hydrogen is written as H1 and neutral iron is Fe1, or hydrogen 1 and iron 1. When an atom contains a different number of electrons and protons, the atom is called an ion. The process of creating an ion is called ionization. Ions are greater by the atomic number, or by the atomic symbol following the Roman numeral, than is 1 greater than the number of missing electrons. Positively ionized hydrogen missing its 1 electron is denoted by H2, while positively ionized iron with 7 electrons is denoted with iron 8. Note that the negative ions also exist, in which nuclei have more electrons orbiting than they have protons. Be careful not to imagine electrons as miniature planets orbiting around the nucleus as a miniature sun. Protons, neutrons, and electrons are not tiny solid bodies. Rather, like photons, they all have both wave and particle properties. The science that accurately describes this complex behavior is called quantum mechanics. Quantum mechanics explains that electrons or atoms can exist in only certain allowed orbits around their nuclei, except when they are making a transition from one allowed orbit to another. These orbital conditions are completely unlike planets, which can exist at any different distance in any orbit around the sun. Each allowed electron orbit has a well-defined energy associated with it, and every different type of atom and molecule has a unique set of allowed orbits. These orbits and their transitions between them are the key to understanding the spectra that we have been discussing. Transitions in a quantum mechanical orbit are only allowed between 2 of the allowed energy levels. These energy levels are the same as the energy of the photons that are emitted, or the change between these different energy levels are the same as the photons which are emitted. So, for example, you have the Lyman series in the middle, written in green, which is going to tell you a certain amount of which spectrums or which allowed frequencies or which allowed wavelengths of light are allowed, because as you move from n equals 1, which is the lowest energy level or the ground state, to n equals 2 or n equals 3 or n equals 4. The similarity between the absorption and the emission lines are explained by these quantized energy levels, in that atom or an electron can only jump from one energy level to the next if it has if the photon that's exciting it has the energy that is equal to the change in energy from one energy level to the next. Also, as the excited photon comes back down, it is going to emit a photon which is going to be at that same frequency as the absorbed photon would be. In 1842, Christian Doppler, a professor of mathematics in Prague, deduced that wavelengths, hence color, are affected by motion. As an object moves towards or away from you, they change color, an analogy to how the pitch of a siren changes as it passes you. As shown by the observer on the left in figure 415, which is on the left, the wavelengths of electromagnetic radiation from an approaching source are compressed. The circles represent consecutive wave peaks through emitted in all directions. The position is slightly closer to her. She sees shorter wavelength than she would if the source were stationary. All of the colors in the spectrum of an approaching source, such as a star, are therefore shifted towards the short wavelength, blue, end of the spectrum. Regardless of the distance, this phenomenon is called blue shift. Conversely, electromagnetic waves from a receding source are stretched out. The observer on the right in figure 415 sees a longer wavelength than would be seen if the source were stationary. All of the colors on the spectrum of a receding source, regardless of distance, are shifted towards the longer wavelength, red, end of the spectrum, producing a red shift. A blue shift or a red shift is also called a Doppler shift. The amount of Doppler shifts varies directly with approaching or receding speed. When the speed are small compared to the speed of light, an object that approaches twice as fast as another has all of its colors or wavelengths blue shifted twice as much as does the slower moving object. How much this wavelength changes, lambda minus lambda initial, or delta lambda, over lambda initial, the wavelength that is initially emitted from the moving object, is equal to v over c. From here, we are able to determine the radial velocity by looking at how much a common element or a common spectrum of absorption or emission is going to be shifted using the Doppler shift as it moves away from or towards us. However, we are unable to directly measure the transverse velocity without first knowing the angular velocity and the distance between the observing party on Earth and the star or the planet or whatever we're looking at in space. Also, using the Doppler shift, we can tell if an object is rotating because one side of the object will be rotating away from us and another side of the object will be rotating towards us. Doppler measurements of planets, the sun, and other stars also reveal that many of these bodies are rotating. Rotation is deduced when the Doppler shift shows that half of the surface is heading towards us while the other half is simultaneously moving away from us. Furthermore, Doppler measurements reveal that all of the very distant galaxies are moving away from us, meaning that the universe is expanding.